All right, so here we are continuing on with forces. So we're going to dive into specific types of forces. You've just seen the Newton's 3 laws. You've seen free body diagrams. Now we're going to talk about each individual kind of force. What do they do? What are they? How can you apply them to a certain situation? So today we're going to talk about law of gravitation. So gravity attracts any two objects, and it depends on their mass and their distance apart. You will notice on the set of notes that I've given you, there are blanks that you can fill in as we go. Does anyone not have the set of notes? Okay. So any two objects that have mass, they are going to attract something else with mass due to gravity. So, believe it or not, you are attracting the person beside you towards you using gravity. I like to use that as an excuse why two people like to sit very close together, although there may be other intentions behind that. Yeah. So the actual equation of this is this. So F with subscript G, this is not F times G, F with a little g to say it's the force of gravity, is equal to capital G, make sure this is capital M, lowercase m, over r squared. You will sometimes see this written as m1, m2. You just need to distinguish that these are two different masses. They're not the exact same thing. Do you remember what the equation I said force of gravity was in the last unit? Yeah. mg, yeah. So force of gravity was equal to mass times g. This is more general. So by universal law, it means it works everywhere. So G, capital G, is what's called the universal gravitational constant. You don't really need to know that. You just need to know that this is what the number is. It's a number. It's a constant. This will never change, and this is given on your formula sheet. So some of you, I think, kept the formula sheets from the test last week. Okay. I will give them back to you because you can keep these. So on the back of the formula sheet, I have this constant. Do not memorize it. It's a waste of brain space to memorize it. If you use it often enough, it'll just be stuck there. Notice the units for this. Okay, this is just to make it so that this equation works with the units. But again, that's on the formula sheet. You do not have to have that memorized. M is mass of the first object. Lowercase m is the mass of the second object. And notice r is not the radius. This is a very common misconception with this. R is not the radius. R is the distance between the two centers of mass. And I will specifically show that in a later example. But for now, I want you to write this down. So two m's correspond to the two different masses. And r is the distance between the centers of mass. So for instance, if I'm talking about two planets, and we want to look at what's the force of gravity between them, I need to compare between the centers of the planets, not from the surface of the planets. That's essentially what this means. In some cases, r might be the radius. So for example, all of us sitting on the surface of the Earth, if I wanted to know what's the force of gravity from the Earth, it's going to be the radius from the center of the Earth to us. So every now and again, it is a radius. Most of the time, no. Everyone got this written out? Yes? Well, it should be fairly obvious which box goes with which. So there's a box for an equation. Put the equation in the box. There's a spot to put all the different variables. Put the definitions there. Yeah. So let's give this a go. So what is the force of gravity exerted on a 70-kilogram astronaut that is standing on the Earth's surface? I give you these values. These are also going to be on the formula sheet. Please do not memorize them because that is not going to be of any importance to you. But we can actually go about solving this. So we have our equation. Whoops. So we have our equation here. We've got that Fg is equal to capital G times capital M, lowercase m, over r squared. And we have everything we need. We know what capital G is, 6.67 times 10 to the negative 11. We've got mass of the Earth, which is normally the big M. That's why it's nice to write a capital big M for the bigger object. Lowercase m is our astronaut. And the distance between their centers of mass is essentially this. So technically, we've got the radius of the Earth and then a little bit of a radius to go to the person's center of mass. Very small compared to the radius of the Earth. So it's basically negligible. So we're just going to plug all these numbers in. So 6.67 times 10 to the negative 11 times the mass of the Earth. We have this value times the mass of the astronaut, which is 70, all over distance between them squared. Yes. Power of negative 11, yeah. This is the constant from the previous slide. Yes. For the force of gravity, what's the unit? Yeah, so any force, the unit is newtons. 70. Yep. If there's something that you can't tell what the writing is, please let me know. Because this thing doesn't track writing all that great. From here, you will want to try and type this in your calculator because you might not be familiar with doing times 10 to the power of something. These are just really large numbers. So you will want to make sure that you get good practice trying this out. So I'll give it a try. You can double check and make sure you get the same answer. I highly suggest you do this. Where did I get my calculator? Canada. You can get them here. They're just over 1,000 pounds. So I don't suggest it. That's what I got. 685.9 is what I got. I'll give you a sec to try this because I really want to make sure you can put that in your calculator. This is going to be a simple version of this equation. So please give this a try and make sure that you can do that. Well, this is the simplest version of typing out mg, or force of gravity, yeah. Other times I'll give you the force, you need to solve for the radius. Another time I'll give you the force and the radius, you need to figure out one of the masses. So you're just rearranging this, but you really need to know how to plug this in your calculator. If this, pardon me? What will help with this is if you put the brackets like I did. Having brackets helps to segregate different parts of this. Especially when you're putting in the squared in the denominator, having a bracket helps. Calculators are smart, but they can be dumb at times too. Did anyone else get this? Yeah? Yeah? Yeah. Give you another minute to try this. This is going to be the only time I'll give you a chance to try out the equation, so please take advantage of this. Did it work? Yeah, good. You got it? Perfect. You'll have to turn it sideways and be able to use the brackets and the powers. So you have to unlock your phone to be able to do it there. It does work. It's better on another calculator. All right, I'm going to move forward. So what is the force of gravity acting on this astronaut who is now at an altitude of this? So how is this question different than the question we just did? Okay, so we're still dealing with Earth, so we are actually given it's the same mass, the same radius as the last question. What do you think? So we got a different radius. You're told this, well, what is this number? Or more importantly, what does altitude mean? Yeah? The height from? Yeah, so this is the height from the surface of the Earth. So in the last question, we had our Earth, we had the person standing on the Earth. This time we've got our astronaut is out here floating in space, and we're told that between him and the surface, this is 6.38 times 10 to the 6. So that's that distance. Plus, we also have this distance. So this again is 6.38 times 10 to the 6. So this is the radius of the Earth. Not squared, because we want to add them together. So this total distance from the astronaut to the center of the Earth, this is my R value. Again, don't think of R as radius. Think of R as distance between centers. So I'm now going to do this, except my radius has changed. So I want, what's the force of gravity for this? So I'm going to use the exact same equation. Still going to use this. My gravitational constant doesn't change. Still 6.67 times 10 to the negative 11. The two masses don't change. What was it, 5.98 times 10 to the 24? Was that the same as the, is that the mass of the Earth? Perfect, okay. Times the astronaut, which is 70. All over. You can tell we use this mass regularly because I've got it already in my head. So now if I'm doing the radius, I need to do 2 times this. So either you can just add these two together or times it by 2. I'm not going to put times 2 in this case, even though that's easier, just so you can see where it comes from. But you could just times it by 2. So I'm essentially just going to add these together to get my total radius. If you would like to just add this together on the side first, so first figure R is equal to these two things added together. If you want to solve for that first, and then put in the number so your equation doesn't look ugly, go for it. Okay, it doesn't really matter. I'm just showing you where this all comes from. Questions with this? Or are we good so far? Yeah? I put them both because I want the altitude plus the distance to the center of the Earth. Because remember, the R value is distance from center to center, not center to surface. So I always want them to the two centers. So now plugging this into the calculator, let's see what we get. 171.4. Okay, let's see if that works. I got this. Perfect. Again, if you want, you can try and plug this into your calculator and see if this works. But this is what you should get. Yeah. So you need to be very careful with your questions and read it carefully. Don't just see a distance and say, oh, that's my radius. Because this is not always the radius. So take a look at what is the altitude or what is the distance above the surface. Okay, we good with that? You're good? Yep, I did that. Is this my last example? No. Okay. So like I said, yeah. We will get to experiments, yeah. Yeah. Newtons are the units. So like I said, you and the person sitting beside you, there is a force of gravity pulling the two of you together. So let's actually give this a try. So if I've got two physics lab partners sitting side by side, we've got one of the mass of 65, one of the mass of 55, and if they're sitting 50 centimeters apart, which is not COVID regulation distance, but oh well, what is the irresistible force of attraction between them? So we're still using the same equation, and we're going to assume that the 50 centimeters here is from center to center. Exact same equation. I'm going to stop writing out what capital G is. You know what the number is, but I'm going to stop because I don't need to write it all out. It's a constant that stays the same. So G I will leave as such. Capital M, lowercase m, it really doesn't matter because multiplying them in reverse order won't make a difference. No, if you put it like this on the test, I'm fine. If you just write it out as G in your equation, I will assume you know what the G is. But all the other numbers, please put in. And then we've got our radius, oops, not a 6, of 50 squared. And then we'll go about solving this. Yeah. Yeah, those are on the formula sheet. G is on the formula sheet. The mass of the Earth, the radius of the Earth, that's all on the formula sheet. Checking to see if anyone's awake. Yeah. I should have a bunch of people saying something's wrong with this. Yes? Nope. 50 at the bottom. Why is the 50 at the bottom wrong? No. So R is the distance between two objects that we're looking at. What's wrong with this? Needs to be in meters. There was quite a few people when you were doing your kinematics assessment who got numbers in kilometers per hour and tried to do the equations and they don't work. It needs to be in meters, it needs to be in seconds and kilograms. So this would give you a wrong answer. You said 55 needs to be 50. Oh, yeah, okay, sure. Just like everyone knew it, they just didn't want to put up their hands. Yeah. We'll get to the answer. I'm not there yet. So how do I turn 50 centimeters into meters? Yeah, so you take this, divide by 100. Yeah. Don't forget to square it. Very common mistake is to forget the square. Oh, yeah. Okay. So I got this. 9.54 times 10 to the negative 7. Anyone else get that? Okay. What does the time 10 to the negative 7 mean? Yeah. So it's going to be, this decimal is going to move 7 places to the left, meaning it's 0.000000954 newtons. Why do you think this is so small? Because think about the other ones we had. So we had 171 newtons. We had almost 700 newtons. Why are we all of a sudden dealing with a very, very tiny number? What do you think? So they're sitting close to each other, so you think the distance, if the distance is smaller, your number should get bigger? So if R is smaller, does that make the force bigger or smaller? Yeah. So if R is smaller, the force should be bigger, but yet this is not a bigger number. Mass. Look at our masses. I've got 65. I've got 55. What's the mass on the other one? Times 10 to the power of 24. So I've got a power of 24 times larger mass. So the mass plays a huge role in this. So this is why when you're sitting next to someone, you don't actually feel like you're starting to move towards them. It's very small. You barely feel it. You feel more pull towards the center of the earth than you do to the person beside you. So therefore, you're not falling over, going closer to someone. Once, whoever just left came back. I forget who it was. So there are experiments where you can test this out. I've seen one where they do kind of like a time lapse, where they've got a, what is it? They've got like a bowling ball that's suspended from the ceiling, and then they have another bowling ball on the end of a long stick that's suspended, and they just leave it, let it go, and then over the course of time, the bowling ball moves towards the other one. And then they tried it from the other direction, and it was the same thing. So it wasn't, the floor wasn't slanted or something like that. The gravity does pull it towards there. So it's hard to find an experiment like this, just based on the fact that you need really big masses to be able to see it. So that's why you often see it as a over time something. Yeah. No, it doesn't when you're multiplying them like this. Once we get into the next section, it matters which mass we do, but for here, no. It doesn't matter which you pick as m, the capital M or lowercase m. Okay. Here is a typical problem type that you are going to see in this unit, you are going to see in later units. It is going to be on your test, so you will want to star this because this is guaranteed to be on your test. And you will see it next year if you continue with Physics 12. So this is so typical that you'll want to pay attention to that. Adam, you got that? Did you hear what I just said? What did I just say? You spend an awful long time staring at your calculator. Would anyone else like to inform Adam of what I just said about this question? Yeah? This is on your test. So you'll want to star that. So the reason why this is a typical type of question is because I give you basically nothing. And you're expected to solve for something like this. So you're told an astronaut weighs 800 newtons on planet X. We don't know anything about the planet. We want to know how much she will weigh if she was at an altitude equal to the radius of planet X. You're given no masses. You're given no radiuses. However, you can solve this. So let me show you how to do this. I've got a couple of these I'm going to do. So we've got an original FG. Typically the equation is this, GMM over R squared. Right? I don't know the mass of either of these objects. I don't know what the radius is. However, I do know that this original force of gravity is 800 newtons. So all of these things times by each other equals 800. That's about all I know. So what I'm told is, or what I'm looking for is, what is this new force of gravity if I now say that she's at an altitude equal to the radius of planet X? So this is similar to the question we just did, where we're on the surface of the Earth, and now we're now at an altitude equal to that surface of the Earth. Except now it's planet X. So essentially we're going like this. Here's our planet X. Here's our astronaut. They weigh 800 newtons here. Now we're told that this astronaut is way out here, where this is equal to the radius. The original radius. So what has changed from this equation to this equation? The radius. I haven't changed any masses. I'm only changing the radius. So I'll have G, MM, over, and what happens to my radius? It doubles. I went from R to 2R. So my new radius is 2R. And be very careful with this. You want to put 2R in brackets. The reason I want to put 2R in brackets is because this whole thing is squared. How does this help us? I still don't know masses, I still don't know radius. Well, first I'm going to expand this and then I'll explain. So we've got G, M, over 2 squared is 4, R squared is just R squared. So this is my new force of gravity. Still doesn't make anything clear. But let's take a look at something. Notice what I've got here and what I've got here. What can you tell me about these two red boxes? They're the same, right? Can everyone see that? I've got a capital G, capital M, lowercase m, divided by r squared. So these are the exact same things. And what does this box equal? It equals 800. So if this box equals 800, this box must also equal 800. So I've got 4 in a denominator here, so 1 over 4 times this box, so times 800. So if you go 1 over 4 times 800, you get 200. So I just solved for this entire thing without knowing anything about masses, without knowing anything about the radius, and you can go about solving this. So this is the exact strategy I'm looking for when you are going to solve this. So again, let me walk you through the steps. First, write out your original equation. Write out what the original weight is. Then you're going to need to go through the question and figure out what changes, because I could change the mass, I could change the radius. Find your original equation and substitute in the value from above. And then solve. That's the final answer. So the math behind this is not too bad. It's the strategy that can be a bit confusing for this. Yeah?
Why did you write
because your equation is r squared. So my r is from here to here. Now my total r is both of these combined, so I changed it from just the radius of the planet to 2 times the radius of the planet. If it helps, if it makes it any easier, you could subscript these as rx so that you can tell the difference between those, but that's essentially what you're going to do. So let's try another one. And then I think this is the last one, yeah. This is the last one for today. So now let's try this one. What can you tell from the question to know that this is the type of question that we just did? How can you tell that this is what you need to do and not actually solve for something? You're just given an original weight. What else? So if you see stuff like twice, half, if you're doubling a mass, tripling a mass, if you're halving the radius, quadrupling the whatever, then you're going to deal with this type of equation. So that should be a dead giveaway as to what you're doing. So what is the first step I'm going to do to solve this? What's the very first thing that I did on that last example? Write down the original equation. So I've got Fg equals gmm over r squared, and this is equal to 10,000. Yeah, what did I do next? Okay, yeah. So we're rewriting this for the new one. So this is the new. Yeah, so you said the planet is twice as massive. Yeah. Yeah, so this mass doesn't change over. Okay. Again, be very, very careful with this. Anytime we're dealing with something with the radius, put this in brackets. I cannot stress this enough because if you don't put it in brackets, you're going to get the question wrong. Because it says twice as massive at half the radius. So it just means your radius needs to be half. So again, it's the entire radius squared. So if my radius is half, it's half the radius all squared. What do I do next from here? Substitute? Before I substitute. Yeah? Yeah, so we're gonna rearrange this. It's nice to get all the numbers out front so that we don't have to worry about those. So I'll put this 2 out front because again, it doesn't matter the order that I apply the multiplication. All that matters is that I get it right. So 1 over 2 squared gives you 1 over 4 r squared. And then the next thing we do is we're going to substitute. So again, you don't always need to show this box. I'm going to show it just for the sake of showing you where this comes from. These are again the same. So I can substitute in 10,000. So 2 divided by 1 over 4, that's just 8. It's the same as 2 times 4 over 1, times this box, and this box, which is equal to 10,000, equals 80,000. Again, don't forget to put newtons as your unit for this. Questions with that? Two at the top here, because my planet is twice as massive. So I needed 2 times m to give you the new mass of the planet. Any other questions on this? That's it. All right, so that is the notes for today.